at the conclusion of one event and the start of the other event, we have a joint keynote. And this year, we're quite honored to have Dr. Sarah Pearce, the director of the SKA Low Telescope, to give that talk. She joined SKAO in July 2021 as the director of the SKA Low Telescope, as I mentioned. She leads a growing team in Australia that's preparing for the deployment, commissioning, and operations of the world's largest low-frequency telescope. And I'm sure she'll show us some pictures of what those telescopes actually look like. And they will be built at CSIRO's Murchison Radio Astronomy Observatory here in Western Australia. From what I've been told, a considerable ways north of here. So the first time I came to Pawsey, I thought it'd be really cool to go see the SKA. And I was told it's very far and very remote. And I was like, oh, okay, makes sense. Pardon? 800 kilometers, yes. So it wouldn't be a day trip. Anyhow, so before joining SKAO, Dr. Pearce was with CSIRO, which, as we heard from Mark earlier, is essentially, so those of us from the NSF would equate it roughly with the NSF, although it's kind of an interesting combination of NSF and like DOE laboratories, because you have laboratories and people who are doing the science and not just funding the science. Anyway, so she was the deputy director of CSIRO Space and Astronomy and was the acting chief scientist there from January 2021 until she moved to SKAO. Anyway, so we're very honored to have her here to speak today. As we heard Mark mention earlier, Pawsey is intricately connected to astronomy in general and to radio astronomy in Western Australia in particular. It's a big part of their mission, and I'm sure that we'll really enjoy your talk. So please join me in welcoming Dr. Sarah Pearce.
Thank you very much for that great introduction. I feel like I don't need to introduce what I'm talking about now, but I will anyway. I will start though. Mark already acknowledged the traditional owners of the lands that we're on here today, the Whadjuk people of the Noongar Nation. I also acknowledge the traditional owners of two other places where SKA is working in Western Australia. The Southern Yamatji, who are the traditional owners of the land in Geraldton, where our Engineering Operations Centre is built. And then the Wurundjeri Yamatji, who are the traditional owners and native title holders of the telescope site in Yarimana, Ilgari, Bundara, CSIRO's Murchison Radio Astronomy Observatory, as Mark mentioned earlier, where we are now sort of well into building SKA Low. I pay my respects to any First Nations people here today, and I'll talk to you a little bit more later about our relationship with the Wurundjeri. So I'm here to talk to you about a revolution in astronomy, something that is going to change what we know about the universe, but is also pushing the cutting edge of engineering, and in particular of computing and software. And I'll go through with you some of the massive challenges that we're going to have with what is a software and big data telescope that we're building here in Western Australia, and another one that we're building in South Africa. But I'll start with just giving you a brief introduction to SKA.
What did the universe look like when the first galaxies formed?
What are gravitational waves? How does magnetism work throughout the universe?
Come si formano I pianeti?
How many gravitational waves are passing through me right now?
What is dark matter?
What is the impact of magnetic fields on the formation of galaxies?
宇宙の歴史はどうだったか。
¿Estaba Einstein en lo correcto?
And for me, the most important, is there life out there?
We ask ourselves, what is the most useful thing that a radio telescope can contribute to the answers to these big questions? We are building a time machine. we're looking at what our surroundings were like almost at their inception. The question is, how are we actually going to make this happen?
So, you know about telescopes, of course. We have telescopes that look across the whole range of the electromagnetic spectrum, all the way from kind of space-based gamma ray telescopes, telescopes like Hubble and the James Webb Space Telescope, which work in the optical and the infrared, and then telescopes on the ground. So you can only look really at two parts of the spectrum from the ground. The optical, obviously we've evolved to be able to see that with our eyes, and that's the kind of telescope that most people think about when you talk about a telescope. But the other part of the spectrum that we can look at really well from the ground is the radio part of the spectrum. So wavelengths of meters and centimeters up to just about millimeters can be seen from here. And that's great for us because what it means is that we do not have to build anything quite as complicatedly, heart-stoppingly engineering-based as the James Webb Space Telescope and launch it into space. What we can build, though, is really large radio telescopes here on Earth that allow us to see the universe in ways that you cannot see in other parts of the spectrum. So why radio telescopes? This is the galaxy. In Australia, the First Nations people call it the emu in the sky. They look at the dust in the galaxy and it makes the shape of an emu. If you look at here from the southern hemisphere, and where the emu tilts tells them what time of year it is, when to collect emu eggs, for example. But the galaxy looks very different if we look at it in the radio. And this is what the galaxy looks like in a survey of radio sources done by the Murchison Wide Field Array. So that's a telescope run by Curtin University here, based on the same site that the SKA will be based on, and where the data was processed here at the Pearce Center. And the reason it looks different is because in the radio, all that dust that gets in the way of us being able to see what's happening in the galaxy is transparent. And so you can get amazing pictures like this, which was taken by Meerkat, an SKA precursor telescope in South Africa. This is the galactic center. And you can see these fantastic magnetic field lines coming out of the middle of the galactic center. Streams, one of the most detailed pictures of the galactic center that's ever been taken in the radio. So we can see through things to see parts of the universe that we wouldn't ever be able to see without radio. But that's not the only thing. And in fact, there are two big books, each about this size, which describe the science case for the SKA telescopes. And they cover all these different parts of science, trying to address some of the major questions that we have about what is the universe, how did it evolve? One of the key things that we will be looking at with our telescope here in Western Australia is to look back to the dawn of the universe, at the time when the very first stars and galaxies started to shine, not long after the Big Bang, probably about 300 million years after the Big Bang, but we don't know exactly. This is called the cosmic dawn, or more technically, the epoch of reionization. And what we're hoping to do with the SKA Low Telescope, among other science goals, is for the first time to try and map that era of the universe's history. So we've seen what happened a bit before that with the cosmic microwave background, which Kobe famously mapped. And we can see things that happen afterwards. We can see what happens now. We can see even 10 billion or so years back. But what we've never been able to do is to detect this period in the universe. It's the end of what we call the cosmic dark ages and the time when the universe first started to light up. And I'll talk to you in a little bit about why it's so difficult to do. But the SKA Low Telescope in Western Australia and the SKA Mid Telescope in South Africa jointly will give us a picture across the whole evolution of the universe that we've never had before. some of the things that we will look at will be fast spinning neutron stars, like this one's called pulsars, which spin 1,000 times a second, and which you can use the signals from to understand what is happening between the neutron star and you. So for example, if you look at how the neutron stars are pulsing, the pulsars are pulsing in real detail, you can maybe see the waves that are caused in space-time by gravitational waves. So we obviously have LIGO, the Gravitational Wave Observatory. This is a way of detecting different types of gravitational waves. We haven't been able to see them yet with radio telescopes, but with SKA mid and potentially SKA low, hopefully we will be able to. And then also the question that all the journalists always want to know, of course, and the one that was touched on earlier in the video I showed you, sort of, are we alone in the universe? So the SKA telescopes will be the most sensitive telescopes of their kind in the radio part of the spectrum. So if there are what we call technosignatures out there, things made by intelligent life, we'll be able to push the boundaries of whether we might be able to see them. The universe is very big and very old, but for the first time using SKA, we might be able to detect things, say if they were as bright as an airport radar, tens of light years away from us. So this is part of the science case for SKA. So now I'm going to talk to you a little bit about who we are and what we're doing. And you might ask, why have I got a picture of what looks like, I don't know, some kind of diplomatic thing? This is the signing of the SKA Treaty. So the SKA is an intergovernmental organization, a treaty organization, which countries have to sign up to in the same way that they might sign up to the United Nations or CERN. One of only 2 treaty organizations in the world for astronomy, the other being the European Southern Observatory. This is the Australian ambassador in Rome signing the SKA Treaty, along with his counterparts from 7 other countries. We actually have 11 member countries now in SKA, along with another 5 who are in kind of various stages of joining. And what you can see here is that it really spans the whole globe, from the south to the north, from the east to the west. Unlike many other kind of astronomy or science kind of organizations, you know, this is a collaboration which includes countries like China, who've typically not been involved in this kind of multilateral collaboration before, and has visions of including a wide range of countries from Africa in the next stage of SKA. So it really is about global collaboration in a way that many other science facilities aren't. So in numbers, what's the kind of scale of what we're talking about? So the SKA2, the 2 telescopes, which I'll tell you a little bit about in a minute, will cost around 2 billion euros over their first 10 years. That's construction costs and a little bit of operations. And we will be building antennas and dishes in the 2 host countries, South Africa and Australia. And we will be producing, importantly for this audience, around 700 petabytes of data a year, which we'll have to share with the international community. And I'll talk to you about that in more detail in a minute. So what are we building? Well, you can see one of these here. At full scale, SKA low, which takes up across 74 kilometers of the Murchison, about 800 kilometers from here, as we said, we'll have 131,000 of these antennas, arranged in groupings of 256. And you can see this is an artist's impression here. We're not quite at this yet, but and each of those groupings of 256 is called a station. There will be 512 stations, around half of them in a massive core about a kilometer by a kilometer wide. And then the rest on 3 spiral arms, which, as I say, the farthest distance between them will be 74 kilometers. And this is a radio telescope that will allow us to look between the frequency ranges of 50 to 350 megahertz. So that's that time when we can really look back in history to the early days of the universe and try and understand that cosmic dawn. And then in South Africa, we're building around 200 dishes. So these are more like what you might imagine a radio telescope usually looks like. South Africa already have 64 of these dishes in place with the Meerkat telescope that I showed you the picture of from earlier. So we'll build up to make up to 197 across 150 kilometers of South Africa, of the Karoo region of South Africa. And that's a mid-frequency radio telescope. So it will cover the frequency range 350 megahertz up to about 15 gigahertz. And then we have another site, which is headquarters in the UK. So any of you from the UK might recognize this. This is Jodrell Bank, just outside Manchester. And this is where the SKA headquarters is. So this is where our council meets regularly and the Director General is based. So I've mentioned that this is a software telescope, and I guess that's one of the parts of this that you're probably most interested in. Astronomy has been on a journey with data. Some people who might be in the audience, Max, for example, might remember the days when astronomers would take data and put it on a disk, or perhaps even have it on paper, and then put it on the shelf in their office and come back 10 or 15 years later to look at the data. It's not quite the same as that anymore. So telescopes like the Murchison Wide Field Array and the ASCAP telescope, which is CSIRO's mid-frequency radio astronomy telescope here in Western Australia, are already pushing the boundaries of such big data that we cannot store it. We have to learn how to process it in real time. And this is one of the key things that the SKA is going to have to do. And this is why we work very closely with Pearce, and we're so pleased to have Pearce Centre here and ready to help us with SKA. So how does it work? Radio emissions from objects in the distant universe are received at our dishes or our antennas, and they induce signals in low noise amplifiers, which are then transmitted down optical fiber to the first stage of processing, the central processing facility on each site. We have about 100,000 kilometers of optical fiber, dealing with up to 8 terabits a second of data from the telescopes. SKA can look at 65,000 different wavelengths. And so if you envisage 65,000 different colors of radio light coming from 130,000 antennas, you start to see why this is such a big data telescope. Once the data has been received, we have kind of 2 ways of processing it. The first is the time domain. So we can add the data together to look for things that change in the sky. Those pulsars with their regular pulses that I was talking about earlier, or one-off events like massive fast radio bursts that explode in the distant universe. The other thing that we do is to look at what we call the image domain. And so in order to do this, we take the signal from each pair of stations or pair of antennas for SKA mid, and we multiply it together to make visibilities. So you can imagine 150,000 different baselines, pairs of antennas at 65,000 different radio frequencies being multiplied together to give us the pictures that we need. So this is very high speed GPU and FPGA based digital processing. Once we've done that kind of processing, it then moves to the supercomputer centers, where we will have 2 supercomputers, one here and one in South Africa in Cape Town. And they take that data, that time domain data and that image domain data, and they process it. So for the time domain data, we look for, through millions of potential source, for millions of potential sources every few minutes. For the image domain, what we have to do is take that massive amounts of data, and we have to be able to process it such that we can understand what parts of the data come from the sky and what parts are artifacts from the instrument itself or from the way that we've processed it. And only by doing that will we be able to understand what the telescope can tell us. So that image domain and time domain data has to be processed in real time because it's much too big to store. And then what we do is we distribute it around a series of what are called regional centers. So there'll be an Australian SKA regional center here at Pearce, and there are regional centers around the world. And it's through those regional centers that the astronomers will be able to access the data. So we will observe for them. We'll have operators who observe, and we'll process the data in its first pass of processing. And then we'll share it with the astronomers through the regional centers. And then they will reprocess it and reprocess it and reprocess it, because astronomers will use as much storage and as much processing as you can give them in order to try and extract their science. So this is, if you've probably looked through the window and seen the couple of racks that we have for SKA at the moment. This is the beginning of our journey with Pearce. We have got just a couple of racks for what we've built so far, but in the end we will put our supercomputer here, and we'll work hand in hand with Pearce with the supercomputer as part of the telescope. Essentially, we'll be at a stage where if the supercomputer and of course the software in the processing pipelines is not working, the telescope won't work. And this is quite a step forward for radio astronomy. Now, of course, we are looking at our sustainability. Of the Sustainable Development Goals, we touch on about 11 of those. This is just a picture. So our 90% of our carbon footprint comes from two things: from operating the arrays themselves and from our computing that's required. This picture that you can see, the image showing now, are of the power station, which is currently at the Observatory in the Murchison. This is the power station that runs the ASCAP and the MWA radio telescopes. We'll build our own power station, hopefully with as much penetration of renewables as we can. And we'll also build power stations in smaller power stations in South Africa to run the arms of the telescope there. So obviously, key question for us is how can we minimize our carbon footprint, and how can we be the most sustainable and leave the least impact on the land that we possibly can. So that was the antennas, running the antenna arrays. Obviously, there's running the supercomputing itself. So here we're fortunate in that Pearce is also working very strongly to try and minimize its carbon footprint to make it to be as sustainable as possible. This is a little video of the cooling system in the Pearce, which uses the aquifer, water from the aquifer here, saves millions of liters of water. Pearce, you'll also see, has some solar panels and things. Over time, of course, Pearce is connected to the grid. And so the key challenge will be to reduce our carbon footprint as the grid becomes less fossil fuel based in Western Australia. So how are we getting ready for this massive data influx, data deluge? So most recently, we've done what we call our third data challenge. I don't know if some of you have been involved in data challenges. Large experiments often do this kind of thing. So this was a data challenge that particularly focused on the kinds of data we will need to look at in order to be able to detect that cosmic dawn that I was talking about earlier. So what it provided was 7.5 terabytes of data, of simulated data, which was then sorted through by groups based at 12 supercomputing centers around the world. So there were 234 participants who took part in this. And what they were trying to do was remove all the data that you get in the first layers of what happened in the most recent 13 billion years of the universe's history, to be able to get back to that simulated data of that time of the cosmic dawn. So this was a great example of supercomputing centers around the world and scientists around the world working together in order to prepare for SKA. So once we can do this, what will we get? Well, we'll get 2 telescopes that are by far the best telescopes in their class in the world. So this tells you the comparisons to the state-of-the-art telescopes in low frequency and mid frequency at the moment. And in particular, what I want to point out is the massive difference in survey speed that we will get once the SKA telescopes are online. So we will be able to survey the sky, see what's going on in the sky so much faster than we can at the moment. And it's through those massive surveys that we're able to do things like really understand how many radio galaxies are there, how they evolve, and try and answer those difficult questions around things like dark matter and dark energy. So where are we up to? Well, we talked about the telescope being built around 800 kilometers from here. It's obviously a bit more difficult to build a telescope in the middle of the desert than it is to build it on the edge of Perth. So why are we out there? Well, in the same way that if you build an optical telescope, you want dark skies. In order to have a radio telescope that detects the very faintest signals from the universe, you need a radio quiet area. And what is radio noisy? Well, people, not people, but the things that people carry with them. All your laptops, your phones, your microwaves, your fridges, your cars. Massively radio noisy, and they really drown out those very faint signals that we're trying to receive. So both the SKA Mid telescope in South Africa and SKA Low in Australia are built in areas of low population density. So SKA Low is built in the Murchison region of Western Australia. It's an area about the size of the Netherlands, and it has a population of 120. So it's really low density. It's more than that now that we're there, but that was the original population. And so we have to be able to get away from where people are in order to do the very best science that we can do. Radio astronomers, obviously, we invented Wi-Fi. That's what we say anyway. But we're trying to get away from it now, and that's where we are. So this is going to tell you a little bit about the site itself. So in Yerimana Ilgri-Bundara, CSO's Murchison Radio Astronomy Observatory. The nearest town is Geraldton, up north of here on the coast, about 350 kilometers from the observatory. And the observatory hosts 3 functioning telescopes already. So I've mentioned a couple of times ASCAP, that's what you can see, it's coming in here. CSIRO's mid-frequency radio telescope, 36 dishes, but what they have importantly is a really innovative receiver on the top called a phased array feed that allows the telescope to take pictures of much larger areas of the sky at a time than a normal radio telescope. So it's a kind of radio camera developed by CSIRO specifically for ASCAP. Then here we have the Murchison Wide Field Array, the telescope that took the picture of the galaxy that I showed you earlier. These little spider antennas, this is a low frequency telescope, so a precursor to SKA Low, slightly different type of antenna, but that has done by far the best low frequency survey of the southern sky that exists, and the data of which we will use in order to understand the universe with SKA Low. You need processing, digital signal processing and things on site, but of course you want to be quiet. We've gone a long way out of the way in order to get away from electronics. And so you need to build a building that has a Faraday cage all around it so that the radio signals can't interfere. We already talked a little bit about the power stations. And so that's the Inyarimana Ilgari-Bundara. And why do I call it Inyarimana Ilgari-Bundara? What does that mean? So that is in the language of the Wajiri Yamaji, who, as I mentioned earlier, are the traditional owners and native title holders of the land that we're on. And it was a name given to the observatory site by the Wajiri themselves from a competition. And it means sharing sky and stars. And I think it's a beautiful name because it really, really demonstrates what we're trying to do in the relationship that we have with the traditional owners. So there's an Indigenous Land Use Agreement, which CSIRO and the Australian government have signed with the traditional owners, and which we abide by as we build and then we operate the telescope. And that gives things like opportunities for work for members of the Wajarri community, but also acknowledgements of the Wajarri, for example, when scientific papers from the telescopes are published. So that's a really important relationship for us, and there'll be a video a little bit later where we talk a bit more about that. Of course, the light touch on the environment is important to us as well. So of the area at Inyarimana Ilgari Bundara that we are using, we are using much less than 1% for the telescope itself. So it's really light touch on the ground. But even with that, we need to be careful. So this is a staff member from SKA Low looking for spiny-tailed skinks, which are a species that are on the verge of being endangered, and that we have to, 7 days before we break ground, we have to survey the area and check and see whether there are any spiny-tailed skinks. And if there are, then we need to move so that we're not near them. And there's been just one area so far. They like this kind of rocky ground. We don't like rocky ground because that's very difficult to dig through. So fortunately, we and the spiny-tailed skinks can live quite well together. But they like this kind of rocky ground. So we've had one area where we've had to move the telescope so far. So this is just going to show you a little bit about the international collaboration that has gone into making this work. So I've shown you the three kind of sites, the UK, Australia, and South Africa. But there are 16 countries involved, and in fact, a few more than that who were involved earlier, who've been designing and are now building the parts of the telescope. So for SKA Low, for example, the antennas that we're building, these antennas, come from Italy. The software is being developed by people across all 16 countries, in fact, but much of it is being led out of the UK and out of India. We've got digital signal processing being developed, high-speed digital signal processing being developed in collaboration between Australia and the Netherlands. And we've got other parts of the digital chain being developed between the UK, China, and Italy. And so you can see it's a real international collaboration where we are drawing on the best expertise in the world in any given area in order to be able to build these telescopes. So where are we up to now? We've spent nearly 2 years now building infrastructure. So we built 200 kilometers of roads, around 100 kilometers so far of, we've put in around 100 kilometers of fiber and around 100 kilometers of power cable. And we've put down sheets of mesh. So you will have seen in the pictures that I showed you earlier that these antennas attach onto steel mesh on the ground. We have 100,000 sheets of steel mesh that are being deployed on site. We put down 20,000 of those so far, along with our principal contractor, Ventia. You can see people putting down the sheets of mesh here. So we're quite some way through the building of the infrastructure on which we will put the antennas and the digital systems that go with them. So this is just a video of when we deployed our first antenna on the 7th of March this year.
What we're seeing is the construction of the first antennas for the SKA Observatory low frequency telescope here in Western Australia. SK Low here in Australia, SK Mid in South Africa will revolutionize our understanding of the universe and our place in it. Astronomers have been dreaming of this place for decades, and it's fantastic we're now here.
It takes a lot of work to get to this point. It's just so exciting to have our field techs actually on site, working, putting antennas together, and getting ready to actually install them to become part of the telescope. I'm over the moon that the Observatory make up over 70% of the team. One of the field tech's grandfathers told me that once the Observatory technicians get back on the land will begin to bloom. And I just thought that was one of the most beautiful things.
My ancestors are from here, and being out here is closer than I've ever been with my heritage. Yeah, I love it. It's very exciting, and I'm very interested to see where this will head in the future.
It's just a glimpse of what we'll see a year from now when they're the experts on this telescope.
I have learned a lot. Everyone's happy to depart their knowledge. Everyone wants to tell you about their field of expertise. So I may be a field tech, but I've learned about every aspect of the antenna and where it's happening and going. We're in a beautiful part of the country. You don't get many places like this anymore, so to be able to work somewhere remote that is still so quintessentially Australian is incredible. I'm so lucky.
So that was the 7th of March. This is a video from kind of an insider station that I took a couple of months ago. So this is one of those two groups of 256 antennas, of which we've now put down 4 of those. So we've built about 1,000 antennas from what will be in the end 131,000. So there's a little bit of a way to go. But this is a particularly exciting time for us because this is when we get to test the systems that we've built and that have been designed over a decade by the international community. Now, the great thing about building an interferometer, the kind of telescope we've got, which is made up of lots of different antennas, is that you can start small and build it out to be much bigger. And you can test it when it's small. So unlike the James Webb Telescope, which we do not have to launch into space, and we do not have to cross our fingers and hope that it unfolds all in one go at the end, because we can just build a very small first version. And that's what we're up to at the moment. So as I say, we've built 4 stations, around 1,000 antennas. 3 of those stations are up and working, and the 4th one is having its electronics kind of turned on this week. And that will be our first tiny version of the telescope. We call it AA 0.5. We will continue building then until around 2028, when we'll have built about 307 of the 512 stations. We'll then pause, wait for the international community to catch up and give us some more money. And the telescope will then be available to the astronomers. By the time we get to 64 stations in this, 2026, only 2 years away, SKA low and SKA mid in the equivalent will be the biggest and best radio telescopes of their kind in the world. And you can imagine it's around that time that the astronomers start to become really excited and want us to look at their favorite objects and do observations for them. So that's where we start what's called science verification. So we start doing very early science in partnership with the international astronomy community, looking at things they've asked us to look at in order to test the telescope out, as we still continue to build the rest of it and get ready for proper science in around 2029. So I talked a lot about SKA low. I'll just talk briefly about SKA mid. Everything I have said about SKA low, essentially, you can assume the same is happening for SKA mid. So they're building these larger antennas, dishes, and you can see that they require these 15-meter dishes to be lifted up from the ground. This is a test dish. These are being built in China. This is a test dish being tested in China. And then here we have a picture of the very first SKA dish, which was the big lift for that occurred in July this year. So they've now got one full antenna and they've got another pedestal. And so it's very much like this. They're at very much similar stage that we're at. In that they're getting ready for their first 4 antennas, which will be their version of AA 0.5, which will allow them to test their signal chain. just a couple of extra things to talk about. So I talked earlier about how we're a truly international collaboration. One of the great things that these international science collaborations do is they allow for science diplomacy. We need close partnerships across all the different areas of people who are working towards SKA, between governments and decision makers, as well as between scientists. And this helps build relationships, which can be built on by our diplomatic counterparts. And so we also work really closely with local communities. We've talked about the Wajarri, but in South Africa, there's great work going on with the local communities there. And of course, in Geraldton, which is one of our regional centres, this is a diversification of their economy and the ability to attract new and well-qualified jobs to an area which has been mostly based around kind of resources so far. Now, people often ask about this, so I kind of get out in front of it. There are more telescopes, there are more satellites being launched every year now than there have been in the history of us as a spacefaring humanity. And they're being launched mainly by companies like SpaceX for their Starlink satellites. So they're being launched to provide internet around the world. There are 10,000 Starlink satellites so far. There will be more than that in the long run. We can see these satellites. We can see them in optical, and we can see them in radio. There are two kinds of things we can see in the radio. We can see, obviously, if they turn the satellites on and they're sending and receiving data, we can see that clearly. But we can also see unintentional emissions just from the electronics in the satellites as they go over. So this is a picture in the optical, of course, from the pinnacles here in Western Australia, an exposure that gives you an idea of what the sky looks like now that there are so many of these what we call mega constellation satellites. So we're working in two ways to help mitigate this. We have a collaboration with our optical counterparts from NOIR Lab in the US under the banner of the International Astronomical Union. It's called the Centre for the Protection of Dark and Quiet Skies, CPS. So you can see the little banner, the little logo in the corner. And they're doing two main things. Firstly, working with the companies like SpaceX. These companies didn't set out to make the night sky busy and difficult to do astronomy in. They set out to provide internet to the world. And so they are engaging with us very constructively in how to minimize the interference from their satellites once they're launched. Satellites last about 5 years. And so if we can, the next generations can be better, then that's within the 50-year lifetime of our observatory, well worth doing. The other thing that we do is we work internationally through organizations like the International Telecommunications Union and the UN for the Committee for Peaceful Uses of Outer Space, to put some international structure around this and make sure that everybody understands the consequences of what's happening at the moment. So this is an issue for us. We've gone to where it's very much more quiet, and this still makes it's still quiet for us, but this is something we have to deal with over the lifetime of the observatory. And one of the things that we really have to learn how to manage is this kind of satellite-based interference. Two more things I just wanted to talk to you about. So I always advertise jobs. So in Australia, we've grown from a team of 2 3 years ago to a team of 80. We'll get to about 150 in the end. Please do take pictures of this slide. That's great. We've got a couple of adverts up at the moment. Feel free to, if you're not an FPGA engineer or a network technician, feel free to share them with people who might be. But we've got a lot of recruitment coming up, particularly in our computing and software team. So if you're interested in working on a massive project like this, that's really pushing the boundaries, doing something unique, keep an eye out. We're in partnership with CSIRO for this team of 150. About 80% of them will be CSRO employees. So you can see these jobs on the SKA free careers pages and on the CSRO careers pages. And then my final slide. What is this? I told you we have a very small version of the telescope working. This is data that was taken in July. It's the first images of the sky taken by an SKA telescope, taken by one of those SKA low stations, the very first one that we turned on. And it's a credit to the software teams that we turned it on, and the data flowed pretty much immediately. So what you saw as this went round was the big galaxy, the radio signals from the galaxy. That's the big patch across the bottom. But you can also see things like Centaurus A and M87, which are large, which are bright radio sources in the southern sky. This is just a taster, of course, of what the telescope will do. We'll have in the end 512 stations. We'll have enormously better resolution. We'll have enormously better sensitivity. But this is a brilliant step forward for us. And this is why it's such an exciting time for SKA at the moment, because astronomers first proposed the SKA in the 1990s. So they've been working towards this for 30 years. And we are now at the stage where, for the first time, we have our first small taste of data from the SKA. And just an image that gives us some insight into what it's going to be like in 5 years' time when we've built most of the telescope. So I don't know how often these meetings happen. Presumably you're not coming back to Australia anytime soon, but I will invite you to follow along as we build SKA and virtually stand with me in 5 years' time in the middle of the core when we're surrounded by tens of thousands of antennas, providing data at 8 terabits a second in order to allow us to look back to the very dawn of the universe. Thank you, everybody.
All right, do we have questions? Wow. Okay, Leo?
Yeah, I was just curious, how do you get the water, like the place you are building things that looks quite dry?
Yeah, so we have bores which are sunk down into the groundwater, and so each of the bores comes up into what's called the turkey's nest. It looks kind of like a pond, and so that's actually one of the very first things that we did when we went out in order to start construction, is sink these bores so that we've got water. So yes, yeah, and that's not yet drinking water, so you need a purification system, which we're just kind of putting online. At the moment, our drinking water is shipped out, but we will have a purification system, and then we'll be moderately self-sufficient in water.
All right, so I have a question. So you mentioned, was it smoky skinks?
Spiny-tailed skinks.
Spine-tailed skinks, and so protecting endangered species definitely support that. But I'm curious because you said you have to move a station, and so your telescope is an array. So the position of the antennae is important. So when you have to move a whole, what is the impact on that? How does that impact the results you get, and also how difficult is it to find a location that will provide the same results?
So for each individual station, as long as it's not like right on the very end of the spiral arms, there's quite a lot of flexibility in where you kind of put them. And if we're talking about moving them, a couple of 100 meters, for example, to be out of the way of where the skinks are, that's reasonably straightforward. The bigger change that we made was before we even started building, the Wajiri Yamaji surveyed the whole area for indigenous heritage. So there have been people on this site for 60,000 years, and there is heritage scattered over, so artifacts and things scattered over the whole site. In particular, in the southern area of where we were planning to build, there was an area which was extremely important to the Watery. And so what we did was we rotated the entire telescope, the 3 spiral arms, in order to avoid that area. Now that's sort of the big kind of change that you can only make before you start building, of course, but it gives an indication of the flexibility that you do get with an interferometer in this kind of array.
Okay.
Thank you for an interesting talk. It's truly impressive. You mentioned that there will be scientists vying for time for their favorite objects in the sky, right? I was wondering, so can you adjust the antennas to look at the specific angle, or is it just discarding certain data that because it doesn't fit in the pipeline?
Yeah, so the way it works is we what's called beamform, point the telescope on the sky digitally. So in order to operate an interferometer, you need to add the signals from each of the antennas or each of the stations together. By looking at the delays in how you add them together, you can add them together either coherently, so they all join together one on top of the other, or incoherently, so they cancel each other out. And so by deciding what the delays are in the time, we have clocks that can time to the nanosecond for each telescope. By deciding what the delays are in the time, we can point the telescope. So we don't point it physically, but we do point it digitally.
So that is a question of processing power. So if you had more processing power, you could filter more for more objects. Is that?
So it is certainly to a certain extent a question of processing power, yes, but there are kind of limits to what you can do. I mean, we need to add the signals together to make a station beam for SKLO first, and then through the correlator. So this very flexible telescope, and we can decide what frequency ranges we look at. We can even what we call subarray. So we can use some of the stations or even bits of the stations, but there are limits, and we can't store kind of all possible or even process all sort of possible places on the sky. You digitally do have to choose where you're pointing and then process the data for that particular observation.
Thank you.
All right, this is probably, thank you for the talk, follow-up question to yours. So you can do beamforming, but it's all pointing south essentially. What about the north? Is there will you achieve all the scientific goals just by observing the southern hemisphere of the sky, or is there a true limitation that you can't really point it north?
Yeah, there is absolutely a limitation that we can't point north. So most big international telescopes these days are built in the south. If you're looking at the distant universe, it kind of doesn't really matter where you build your telescope. The universe is sort of isotropic. But if you're looking at the galaxy, it really does matter. And so for things within the galaxy, you get a much better view from the southern hemisphere. The galaxy is above the horizon much more. And so that's why a lot of optical telescopes are built, for example, in Chile, and both SKA telescopes are being built in the southern hemisphere. Having said that, of course, there are things in the northern hemisphere that you want to be able to see and that you can't see from here as well. And so there's a low frequency telescope called LOFAR, currently the best low frequency telescope in the world, which is in the Netherlands. And so we will work closely with LOFAR, and scientists will try and get data from both telescopes in order to be able to, get a sort of more coherent picture, if that's what they need, of objects both in the northern and in the southern hemisphere. And similarly with optical telescopes, a lot of them in Chile, but also optical telescopes in Gran Canaria and Hawaii and things, so the astronomers can apply for time on a range of telescopes and at a range of different wavelengths to try and understand what they're looking at.
So thank you first for the very inspiring talk. I have a question. According to all the 100,000 of components you have, we have the same problem in HPC. Lots of components. There are lots of components failure, and especially as you are running for 50 years, as I understood correctly. How do you cope with these errors, and do you expect to degrade the quality of the telescope over the years, or to improve it because you have improvements in software?
Yeah, so one of the key things for us to understand, now that we've built a few stations and as we sort of build more, is how do we maintain them? So we're currently planning a model where we have a team of engineers who go back to, and technicians who go to each station 3 times a year or so to do housekeeping, I guess. Now, I didn't show you any of these pictures, though I thought about it, but we've had a test array which has been out for a bit over a year, and there's been an enormous amount of growth through the mesh. There are beautiful wildflower pictures among the antennas, which you can find online if you look for them. So one of the things we have to work out is to what extent do we need to garden at the telescope sites. We think in principle that it shouldn't make much of a difference, but these are the things that we're going to have to test. And so yes, we need to monitor. So we monitor obviously every component essentially. Yeah, we have hundreds of thousands of data streams monitoring the stations and the antennas. So what we will do is we'll do kind of gentle degradation. So once a station, if one antenna stops working, we don't really care that much. Station still works fine. Once it gets to a certain level, we'll send out a team to make it work again. Digital signal processing goes through what's called smart boxes, 24 of those on a station. If one of those goes down, we'll probably go fix it straight away. Yeah, but these are all the sorts of things that we have to learn, as we build up the interferometer over the next kind of 5 or 6 years.
Thank you for that informative talk. One thing I was wondering, you were talking about the satellites creating problems. The atmosphere itself changes quite a bit. How much does that distort, and how do you account for that?
Yeah, a lot. So it really makes a difference. And in particular, the ionosphere makes a difference to the radio signals that we've got. And so what we need to do is in order to, for a lot of the signs, but in particular for the cosmic dawn signs, the epoch of reionization, we really need to understand what the ionosphere is doing at different parts of the telescope. So we need to do what's called direction-dependent calibration. But what that essentially means is kind of trying to understand what the atmosphere and the ionosphere is like where you are at the time, so that you can calibrate that out. So yeah, absolutely, it's a major challenge for us.
Yeah, thank you very much for the talk. I'm just wondering, could you tell us a bit about your personal interest in specific science cases that you have in mind? What are you most interested in investigating with SKA data?
Well, this is going to seem like a cop-out, but whenever we build a new telescope, I think the most interesting things are what we didn't know and what we find that we didn't expect. So of the top 10 things that the Hubble telescope found, 8 were not predicted when it was built. Yeah. And that's kind of common for new telescopes. So we're opening up what we call new parameter space. We'll be able to see things in the universe that have never been seen before. And so that's kind of what I'm most excited about, is what's coming that we don't expect. So a really good example is CSIRO's ASCAP telescope. So those 36 dishes that I showed you earlier, wide field of view because of the radio cameras they've got, and that allows them to survey the sky a lot more quickly than other mid-frequency telescopes were able to do. One of the very first science things that ASCAP was able to do, and it won the Australian Prime Minister's Prize for Science, was to detect new kinds of objects called fast radio bursts. So I mentioned those in passing earlier. They're extremely bright, extremely short pulses of radio light, which were first detected with the Parkes telescope in Australia. These weren't known when ASCAP was designed, but because it can do what no other telescope can do, it was perfectly timed, in fact, with the birth of this kind of new field of fast radio burst astronomy, to be able to do some of the first detections of fast radio bursts and the first understanding of where in what galaxies they came from. And so that's a long way of saying it's the unknown unknowns that I'm looking forward to.
One more question.
Hello, thank you. I think it's a follow-up question of one of the previous questions. So during these years of service, I think the antenna, they work by station, right? And how do we think it's scalable? I mean, during, let's say, the 50 years of service, do we plan to build more antennas and more stations to keep up with the technology growth?
Yes, so I mean, every telescope needs a technology development program to go with it so that it can continue to be at the cutting edge. So there are two things for the SKA telescopes and for SKA low in particular. First is scale. So you've suggested, so when SKA was first proposed, it was going to be 10 times bigger than it is now. Now you can already see that what we're building now is like so much better than what currently exists. It's difficult to get governments to pay for something 10 times even bigger. But that ambition still kind of exists. And so CSIRO, for example, is doing tests of what we call very long baseline interferometry using low frequency antennas on the east that they're going to build on the East Coast to test really long baselines through which you can see much more detail, much higher resolution than we can with the 74 kilometers we've got here. The other thing is the technology improves. And so it's difficult to replace the antennas, obviously. That takes a lot of time. Even replacing the low noise amplifiers on the top of them takes a lot of time. But upgrading things like the correlator, which is the digital signal processing that we use to multiply those visibilities together to do the interferometry, that's the sort of thing we would typically expect to do about every 10 years. And that will probably give you the ability to, have more flexibility in what frequency ranges you look at, and in how you use different bits of the telescope together. The software is going to be absolutely critical for us as well. And I think we will spend at least the first 10 years and maybe longer continuously upgrading our software and the processing pipelines that we use in order to get the most out of the data that we're receiving. Every telescope takes quite a long time typically to get to be the best that it can be, even in its initial configuration.